mathematics at U Michigan, and she'll be speaking now and also at the conference in about 2 weeks from now. And she's speaking about gravitational wave memory.
Thank you very much, Jordan, and thanks to the people here at BHI for the invitation. And after we heard a beautiful talk by Malcolm on the blackboard, let me switch as a mathematician to the projector. I'm going to talk about something classical here, so namely gravitational wave memory. And maybe being a mathematician, I would also like to advocate a little bit the different approaches, how we study the memory. I'm going to explain what that is, etc. on the way, but I'd like to also, from a mathematical point of view, explain a little bit what we are interested in terms of what we can extract, how much information we can extract from the Einstein equations. Very briefly, I'll just, I have the mechanical pointer, talk about space-times in general, just very briefly, with radiation, and I will talk about null infinity for asymptotically flat systems, etc. But also, after giving an overview what memory is and all in the classical sense, so I'll say most of the things about isolated systems. So when we have Minkowski as a background and things are decaying fast enough so that we can really treat, let's say, things as isolated gravitationally. But also, the next question will be, well, if you're in a cosmological setting and you would like to observe memory in the future from sources which are really far away, then you have to believe that we live in an expanding universe where there's also inhomogeneities in the background, etc., where these things have to be taken into account. Well, of course, everybody knows Einstein. I thought I'd put a few pictures into my talk. And that one I found, it's the high school radiation picture. Right? You don't see so many pictures of him as a young person, I guess. Anyway. If we are not in a cosmological setting, of course, we all know the Einstein equations, right? So we solve them for asymptotically flat initial data, and as a mathematician, I think of doing a Cauchy initial value problem. I plug in the initial data of some sort that I think is physically relevant, and then we want to construct the whole space-time. And now going to the type of questions that physicists might be interested in, or astrophysicists. Well, what can we observe, for instance, in gravitational wave observation? So what does null infinity look like? And here is the first problem between a difference between asymptotically flat and cosmological. I will come back to that in the last part of my talk. But first of all, if I plug in a cosmological constant, positive, so then, I get the cosmological Einstein equations. And in an asymptotically flat setting, again, so things fall off nice enough, and I have something called null infinity from which I can read off radiation properties of the field and derive a lot of information. And if we now go to cosmological space-times, there's a problem. Null infinity is actually space-like, so what we used to know and cherish for the asymptotically flat space-times is not there. So how do we deal with that problem? And there's a new method or idea I would like to present towards the end of my talk. Before I go there, let's go back to maybe some simple things. So again, maybe this is of course clear that we have a lot of beautiful structure out in the universe. And I just want to mention, of course, we have the Hubble Space Telescope showing us gravitational lensing in some nice frame. So in the cosmological situation where we are really far away from the source, lensing and these inhomogeneities in the universe should play a role. So that's the first thing I say about the cosmological part. Maybe I jump just to a picture. So this is more. So this person is Madame Choquet-Briat. Let me stay with her for maybe a minute. She's really a very interesting mathematician, physicist, and person. She's, I think, now about 93 years old, and she had. If you think about the history of GR a little bit, it's really intriguing. In 1915. Einstein wrote down these equations, and Eddington in 1919 had a first, of course, breakthrough showing the deflection of light with his expedition during a solar eclipse. So there were some physical breakthroughs, and Lemaitre, who derived the expansion of the universe, Hubble, who confirmed things, etc. But the mathematicians were, if you look at what they were doing, I mean, Hermann Weyl jumped on the problem, Hilbert was working it. But if you look at it, just if you browse through a textbook, you think, what were they doing? Sitting on the beach or doing nothing? The thing is, it's really hard to go from this beautiful looking Einstein equations, just this nice curvature equations there, to a well well-posed initial value problem for PDEs in mathematics. And it took a lot of people, Luret, Schauder, Sobolev, it's just a few of them who really worked hard during this time to formulate the initial value problem. And Ivan Chateaubriand, so in 1952, really fulfilled that. So that was the first well-posedness for the Einstein equation, so we can give initial data and show things are well-posed, etc. Well, from there it took a little while, but until we had global solutions in terms of stability. So I cite this one because the asymptotics are interesting. So Christodoulou Kleinemann showed then around 1991 that, well, if you have small enough initial data, you've produced a global solution to the Einstein equations, which is actually, there's no black holes, which is geodesically complete and behaving nicely. So we call this the stability of Minkowski space. Why I'm citing this is because the non-asymptotics are actually independent really from the smallness. You can plug in large data and still of some sort, and the non-asymptotics are still of that type. So we understand well in full details these kind of space types. Anyway, so maybe just a few things. Well, when we think about, of course, black holes merging, etc., so something is going on here locally where the curvature is really, well, where gravitational waves are emitted and things look chaotic, etc. But once they travel at the speed of light along this, I call it like coma, there's of course more geometric structure, null hypersurfaces out to null infinity, then, I mean, nicely enough for us, so certain geometric analytic properties have survived and become really physical observables, and we can read that off and see why we're seeing some of them already. And so I'm interested now in what can we say, first of all, mathematically. So often you have some methods to do an initial value problem. Very often you do, more often you don't have them. So there are other ideas. How can you still extract information for non-asymptotics, for instance, when we don't have these tools? Maybe there are approximation methods and other things we can do. Okay, so gravitational waves, as we all know, are changing the space-time when they travel through, so it's ripples in space-time, as we all know. We can think of the source here traveling on some time-like path, and things are radiation is radiated here along null hypersurfaces out to null infinity. So I'm talking about asymptotically flat situations now. So what is memory? What do we mean by gravitational wave memory? First of all, if this is just let's say something like LIGO looks like, for instance, 3 test masses suspended by pendulums out in space, you would have another experiment where these things are freely falling on their geodesics. So this is the setup. So when, let's assume for simplicity that our wave comes from this direction, then you would see motion in that plane. And what LIGO has detected already, and Virgo, actually what we have seen a few times already, is, well, number one, when the wave packet is traveling through, so you have this instantaneous displacements of the test masses. They follow the geodesics, so you can really see how space-time is changing, which is an amazing experiment. Now, GR predicts that, well, after the wave packet traveled through, if you ask this on the first sight, you would say, well, things should just go back to where they were before. But GR predicts that this is not the case. We say, well, there should be a memory left, which is a permanent change of the space-time that we can see because the test masses are permanently displaced, right? And you can think of that when let's say, hopefully LIGO will see that in the near future, but we can think of that if you are asymptotically in some maybe Minkowski space, the wave traveled through, and after the wave traveled through, so we are still in a Minkowski space but a different one. So that's one way of thinking of it. And so the memory effect is really the footprint in the universe, and in fact there are 2 types of memory. So maybe I go back to the people who really found that. So Zeldovich and Polnareff in 1974 looked at the linearized version of the Einstein equation, and for the first time they derived this permanent displacement that would show, but it's a tiny effect. And then in 1991, Christodoulou looked at the fully nonlinear problem. In fact, he took the last chapter of this 500-page proof of Minkowski stability, and from there he could read off the physics, basically, of this nonlinear, well, it used to be called nonlinear memory from there. So there's a lot of work that has been done in the meantime, but interesting enough, Well, with David Garfinkel, we thought, well, it's kind of strange that, I mean, when we look at...
But there's nothing about that
Sorry?
effect that requires reading the 500-page book.
No, of course not. It's a very simple
it's
thing.
Like
It's
a
very
3-line
simple.
derivation. Yeah.
I agree with you. I mean, the thing is, I agree with you.
And I think that calling it a nonlinear effect makes it seem more mysterious to...
That's what we thought. That's why we don't like that. I agree
Yeah.
with you there, yeah.
The only difference is some kinds of memory are caused by electromagnetic or other kinds of radiation, and some are caused by gravitational radiation. But the memory is linear, and the stress tensor flux through infinity in every case.
I agree with you fully in both what you just said, and I mean it has nothing to do with linear and nonlinear.
I think Dmitri was confused about it after writing the 500-page book.
Well, actually, right. No, the funny thing, he never liked that. Somehow, he never liked that people call it nonlinear because it's really, but the fact itself has nothing to do with it, right? It has to do that. I will just say in a moment, but that something travels to null infinity, as you said, electromagnetic fields and stress. The part of the stress energy that goes out to null infinity will contribute to that.
Right. So it's a
Right.
quadratic term, so it's a linear term. So you could call that. It's fair to call that nonlinear,
Right,
but
it has
it's
nothing
very
to do
confusing.
with it has nothing to do with that. And even Dmitri, I was a PhD student early up to 2007, and even then, I mean, he didn't like that people call this nonlinear. It's just not by chance, but he looked at the full nonlinear problem, and you have what you have is that you have all the description in a physical space-time, basically. You just take that. And now we have much simpler ways of writing it down, which is half a page or a few lines. That's clear. Yeah. So thank you for that, because that leads me to start to say something else. So it has really nothing to do with it. But what is it? Funny enough is that with David Garfinkel, we had exactly the reaction you just had and said, it looks strange. It cannot be linear, nonlinear. And then we thought, well, we found that actually what people called linear, so this is an effect that is due to one portion of the electric part of the Weyl curvature, and which changes over time. And that's actually a small effect. So what we call a null memory, so if you go to the pure Einstein vacuum equation, so this is really related to, this is the energy which is radiated away up to null infinity, and you can express that in terms of the Bondi-Hughes tensor also. And so that's a very, in the end, a simple formula at null infinity, and it has nothing to do with linear, nonlinear. And so then David and I, well, there's many people who, after the pioneering results, came up with explanations, especially Kip Thorne, for instance, wrote down things in a different language, and so there are simpler ways of thinking about that. To just mention a few, and I don't want to go too much into detail. I mean, Andy, Malcolm, together with many other co-authors, have done a bunch of, branching off into different fields, etc. also. So what we also thought is, what about electromagnetic fields if you couple Einstein to Maxwell? And with Yao and Ponicenzo, we found that this contributes to the null memory. And that's exactly part of the stress energy that goes out to that. The same we did for neutrinos. We modeled them, so we said, well, let's do things idealistically and model neutrinos by some null fluid. And also there we get a contribution which enlarges this null memory. And basically it boils down to, if you have a stress energy tensor that behaves, like, let's say that decays like r to the -2, or it behaves in a nice way, it will contribute to the null memory as long as it gets out to null infinity. And there is also, you and collaborators, you derived the angular momentum memory as well, which is really interesting. And also there you have two parts, right, of ordinary and null that you can distinguish. So there's a lot of interesting recent research in all these directions as well. Maybe one thing I'd like to mention, and so because this has nothing to do with linear and nonlinear, also David and I thought, well, let's look at the pure, simple Maxwell equations, which are linear, of course. And what we found is that there are two analogs of memory as well. And here it's much even simpler. You can explain that to any friend or colleague who has no idea of GR. So you say, well, if I look at the components of my electric magnetic fields in the Maxwell equations, and maybe I have some components on a sphere and then radial components. If I look at the radial component of the electric field, that will cause an analog, and I haven't said yet what that is, of ordinary memory. And if I look at, again, let's say J, the current, everything that goes out to null infinity, so that will cause an analog that would compare to the null memory. But now, as things are a little bit different in how you measure things in GR, the gravitational waves, but this is just the nature of how you do measurements. So because in a detector, when you would do an electromagnetic experiment, you would have charged test masses, and so they absorb energy from the wave. Just by the nature of that, you don't measure displacement, but you measure velocities. And what the two analogs of memory are in the electromagnetic Maxwell case is really you get a residual velocity, a kick, in a direction where you wouldn't expect that, right? So that's the analog to that. And so of course you can ask many things about, well, quantum theories, and okay, Andy and Malcolm has just talked about taking things much further into exploring other things, so looking at soft particles, etc. So I'm not going into that. I want to stay in the classical field. So
soft is classical.
Yes, it is, but I mean, let me say, yeah, it is classical, I agree. But I want to stay with the purely gravitational wave effect in the old way. So there's a lot of, I hear you just published a nice book, right, about the whole theory taken further. So
well, it's a book. I don't know if it's nice, but
I haven't seen it yet.
But soft is classical gravity waves.
Yes.
It's just in a different, just in momentum space.
Right. Very good. So that's maybe a very short overview, and I apologize because there's many more authors nowadays and who work on that, so I cannot go into all the details here. Instead, what I would like to do is say a little bit more about how would one measure memory, and then come to the cosmological setting where there is still a problem. We have not talked about that yet. So this is another simple equation, just a Jacobi equation. So if you want to see what LIGO does, so you can measure, you have two derivatives here on this side, which is given by the curvature on the right-hand side. So you want to measure displacements between the geodesics, where these test masses are floating. And so you do that by investigating what's going on here. And again, being a mathematician, I want to make a point here. So there are various ways how one can probably nowadays also look at what's that exactly. It's a very simple way to understand that. And if you assume, for instance, a lot of decay at null infinity or certain nice properties on your space-time, then you really don't need that much of work to really understand what's going on. If you go more general, for instance, and you would like to understand more structures in the gravitational waves, not necessarily memory only, but just about the radiation field, then you have various tools. I mean, you can do certain types of perturbation theory often, there's other things, but from a mathematical point of view, I would say, well, I'm interested in initial value problems, but we are not there yet to solve all these problems. But depending on how general the data is, or how interesting initial data you might have, so the non-asymptotics might really change depending on that. And so there's a lot of, I think, mathematical, beautiful work that still has to go into that, not necessarily for the memory, but for understanding what kind of null infinity we get. Anyway, so very briefly, so if this is a distance, a permanent displacement that you would see in a detector, it's on the right-hand side. This is just a formula. I don't explain what there is, but so there would be an ordinary and a null memory, and they are sourced by what we have said. One is going back to just a component of the curvature, changing over time. The other one that should be observable is sourced by anything that goes out to null infinity. So let's go to the cosmological frame. So if we think we are in an expanding universe, even at accelerated rate, there's various things we can do. I mean, if you want to think about a simple model, we can just look at de Sitter space-time, or FLRW. And if you want to do a more realistic model for really faraway sources, we do have to take into account all the inhomogeneities in the structure. So I'm going to say a few words about that. Now, we know that de Sitter has a very nice simple metric, and something even better, it's conformal to Minkowski space. So with David Garfinkel, we also, really in the spirit that Andy just mentioned, we don't want to do all the hard let's say the a lot of machinery to get out something you can do in an easier way. So we were also trying, or sometimes you don't have the machinery and you want to get out something in a straightforward way. So we developed some gauge invariant ways, or focus on some gauge invariant ways of doing perturbation theory. So what we like about this is we really sit on the quantities like the curvature, which are gauge invariant, and you don't have to worry about doing metric perturbations. Anyway, in a situation like that, one can, in a de Sitter space-time, you can bring things back to something like we do it in asymptotically flat space-times, and we found, Yao, Garfinkel, and I, we found that in a de Sitter space-time you have to multiply the energy which is radiated away to infinity, which involves then, which goes into the memory effect, by a factor involving the redshift. So the redshift comes into the game. And if we think about FLRW, maybe very briefly, FLRW, that was, maybe I'll show it here, Wald and Tollish, but Wald and Alex Tollish also did some, with another method, looked into that problem, and also they found that actually you have to multiply with respect to, if you look at the memory with respect to a Minkowski background, you have to multiply this with a redshift factor of that type as well. But now, as I said, well, FLRW, if you think of this in the history of the universe, so our universe has evolved away quite a bit from this homogeneous, nice looking space-time. So there's a lot of inhomogeneous or inhomogeneity to take into account, and how do we address that? Maybe the result first, and then I tell you a little bit of how we got there. So with David Carter and Eunice, we thought, well, let's look at gravitational wave memory in such a lambda CDM model. And so what we found is that we should actually, so we used a short wavelength approximation for that. So in nonlinear optics, so people do this all the time, and Yvonne Jacques-Brouillard has a nice chapter in her book about some other, she uses it for other things, but something along those lines. So this is a very well-known technique. But we thought, well, if you stay, let's say, we distinguish between, we are closer to the zone and far away, so one will be the wave zone and one the cosmological zone. And we find that if we are close enough, we call this the wave zone, then, well, things don't look so different from having a Minkowski as a background, but things look very different if you are far away from the source now. So in the cosmological zone, not only the redshift comes into the game, but we have a factor that changes the memory and actually the wild tensor in general by lensing. It's weak gravitational lensing that comes into the game. So the last maybe 2 minutes, so let me just...
could you also look at it at Scry?
That's the thing, right? So let me explain that in the following way. So if you look at, let's say, a cosmological space, right? Scry is space-like, or null infinity is space-like.
Right.
So
but waves still pass through it. So
yes, exactly.
So you could ask whether.
Right.
What would you ask exactly? Right.
Right. That's the problem. So maybe 2 remarks about that. I mean, people like Abiyash Dekar, Volker Schlee, etc., have been really interested lately in trying to see what would be the equivalent of a Bondi mass in such a space-time, or how do you make sense of what would be this infinity, or what would be Scry in that sense? And I think there's just not much known at this point. Really, we don't know almost anything. However, what David and I thought, well, our perspective is, well, we do not have to go there to say something, because we live in a space-time domain where the scaling is really in our favor, meaning the wavelength is really small in respect to everything else. So we do this short wavelength approximation that gives us what we need. So what we do is, well, let's see, we consider a background solution of the Einstein equations with a cosmological constant. And, well, of course, we have some fluid sitting in there. And we do a perturbation of the following type. So a high frequency or short wavelength perturbation in that sense. So we have the background, and then we add a perturbation where our omega here is not only the frequency of the perturbation, but it's also the inverse amplitude in that sense. And different from maybe other perturbation approaches, we do not stick with that and expand that up to a certain order. Rather than that, we look at the equations and we solve the equations up to a certain order. So that's of omega. So that's different in the philosophy of the other approaches. And yeah, so it's gauge invariant, but maybe I should jump to one or last slide. So interesting enough, so if you look at that, you have the gravitational perturbations, but you also perturb the fluid, and if you think of this at the first time, it could be a real mess. But interesting enough, so we could show that the two perturbations decouple up to order omega to the -1, which is good enough for what we want to see. So with other words, we could just add a pure gravitational perturbation and get everything out of it that we need. So when we do that, so because these two perturbations decouple, we're actually able to do a quite simple computation. I'm not going to show you that, but maybe something else here. At some point when we use this method, so we go and say, well, let's see what the astrophysicists actually observe or know about it. And that's a paper by Spergel, Laguna, Larsen, and Eunice, where they look at this inhomogeneities actually. And so if I count, if I denote now by phi psi some matter inhomogeneities, I can construct some quantity here where the zeta depends on these inhomogeneities. So I have a term that depends on the inhomogeneities that comes into, so by the way, this is the paper, this is out of this paper I just cited. So this would be, through this inhomogeneities, you can actually compute weak gravitational lensing, which is this term. This is due to the ordinary Sachs-Wolf effect, which is small in that setting. But the gravitational lensing here is actually large enough that this will actually affect things in an interesting way. So this is what we gain from the astrophysics. And when we plug that into the equations, right, we have the wild curvature part that is now multiplied by a term where the zeta captures all the information about this inhomogeneities and this weak gravitational lensing. So when I do that, so maybe just 1 minute to round things up. So what we find in the end is that this memory I can now think of, gravitational waves are sent out at, let's say, some r equals 0. They are observed for the first time in the wave zone at r1, and for a second time in the cosmological zone at r2. And what we get is now that here in the cosmological zone, this memory is enlarged it is multiplied by the factor with redshift, but also with the factor including the Sachs-Wolf and the gravitational lensing effect. And of course, this can go either direction, can be magnifying or decreasing. So maybe here. So this is, maybe if you just want to look at that, if this is a way, if I capture, let's say, I can write down a memory tensor in the cosmological zone, so I can compute that from memory. We can compute in the wave zone times that, where this is just a redshift, and this is the tensor. This is the tensor that involves really the inhomogeneities, the weak gravitational lens. So maybe I should stop here. Thank you very much.
So, are there any questions for the speaker?
Yeah.
So, this weak lensing effect that you're talking about, which is just perturbing this the matrix or the tensor that propagates the signal from there to here.
Right.
Now we know that weak lensing also modifies just the basic LIGO signal, right? Just the amplitude of the signal will be either increased or decreased.
Right.
And now you're saying the memory signal is also increased or decreased.
Right.
Is it the same transformation for both, or do they transform differently?
So first of all, maybe one remark first. I mean, the memory is a cumulative effect, right? So when it's like, you can think of it as almost a step function during the time the wave packet is traveling through. So I mean, it's during this fraction of a second where the signal is received. On top of that, so your cumulative memory is adding up. So you are, let's say, if you want to look at it in this nice spectrum that you have, so you will be at the different level at the beginning and at the end of that.
Sure.
So right, and so in that sense, so the cosmological, the inhomogeneities, the weak gravitational lensing that comes into that is also, I mean, it's a cumulative effect in that, right?
No, I understand all that.
Okay.
So at the end of the day,
Yep.
let's say instead of getting a 1 centimeter displacement, I get a 1.5 centimeter because of this cumulative
Right.
effect. Then if I look at the actual LIGO signal, from the merger or whatever, would that also be enhanced by the same 50%? Because the signal from the source is also being lensed.
Right. So the thing is, the way I didn't show that here very precisely, I don't have time, but so the way it happens, it's really, the signal itself is affected as well, yes, but what you have is really the wild curvature, which is sitting there, which is multiplied then by a factor where this lensing is part of it. So that's so the signal itself is enhanced as well, or affected, can be either focusing or defocusing, right? So yes, it is affected by that. But whereas so here, if you look at the geodesic motion of this, right, you integrate basically this Jacobi equation twice to get this permanent displacement. So I cannot say on top of my head what the percentage is, but the thing to look at is really it's the wild tensor multiplied by that effect, which affects the signal itself as well as the memory.
Okay. Because if they're independent, I think it's going to be really important.
Yes, right.
Right, because lensing is one of the things that's a bit of a nuisance
Yes.
for people who want to interpret LIGO events.
Right.
If there's an independent way of assessing
Right,
the effect of that lensing, that would be extremely useful.
right, yes. Thank you.
Can I ask?
Yeah.
So we have LIGOs detecting these black hole mergers and also these neutrinos or these neutron star mergers. And so maybe Christodoulou-Kahneman or Christodoulou's original thing would speak to the first, and your stuff with David Garfinkel and also Koenig and Yao would help with the second. But could you speak to is there a difference in the sort of magnitudes of the displacements between these two circumstances?
Certainly, I mean, in some sense, I mean, the question is always how much energy is radiated in the black hole, right? So you have maybe 4% or so of the mass is radiated away, well, some typical black hole merger. And then the question is, well, how much is radiated away in the neutron star binary merger, and how much of the electromagnetic field can really get radiated away, that it affects the memory, and how much is neutrino? I think, yeah, we need some numbers also to really compare that effect. I mean, there is probably in terms of mass, yeah, I mean.
But it's not like you could add two different things up, right? It's all in the Zildovich and Polnarov or the Bruginsky and Thorne, which gave a more explicit formula. There's
What
something
do you
missing
mean?
there.
What do you mean?
The whole size of the effect is
Of which effect?
the gravitational memory effect.
Well, there's different types, right? If you look at the pure black hole merger, if you assume there's no accretion disk, so then you have just the two types of pure gravity memory. So which is which Polnareff and Christodoulou, right? So there would not be a contribution from any electromagnetic field or neutrinos or anything. If you assume that there is nothing like an accretion disk, for instance. And angular momentum.
There's a precise statement that it's the change in the third derivative of the incoming and outgoing quadrupole moment of everything, and that incorporates everything. So you can take these things and divide them up into different pieces and give them different names, but at the end of the day, there's just one formula.
So if you do that, I mean, the quadrupole moment you can describe very well in the approach. If you linearize and do that kind of approach, you can describe the ordinary memory like that. But so mathematically, you're
No, that includes the full memory if you take the asymptotic incoming state.
But there are problems with the source actually. So if you want to do the full nonlinear memory or the null memory with that, so if you do this kind of approximation, you get something which is not accurate actually.
Well, maybe we disagree because it's a long wavelength effect, and that's the beauty of it. That you can compute it all. The Bruginsky-Thorne formula is exact. If you know.
Well, that's not the same. Oh, okay. So you're talking about the Bruginsky-Thorne. I mean, Zildovich Polnareff had. Then Bruginsky-Thorne.
Zildovich and Polnareff, let's forget. Okay, but for example,
that's a different thing. Yeah, they have a formula where both gravity effects are in there, right?
Yeah. So it's only one thing. You don't need to. If you look at it the right way, it's only one thing.
Okay, I think the beauty is really the structure of not identifying them. Yeah, I mean, it depends how you compute it, and then you get one formula, but it's really, in the end, it gives you the same observable, but I would like to understand what causes it, and there are two different things, really. When if I do it the way Bruginsky-Thorne does it, it's all summed up. But if I look into the structures, again, I'm a mathematician, I go a little bit more into the geometry, then I see that there are two different ways that these are sourced. And in that sense, if I look at the electromagnetic field coupled to Einstein or neutrinos radiation. So this is really contributing to the null memory in that sense.
Right, but those different things only contribute through their different contributions to the stress energy flux at infinity.
Yes.
So it's all comes in the same way from the stress energy flux. It's just that the stress energy flux has different sources.
Right, but
Electromagnetic gravity,
right.
neutrino.
But here I would like, so here I'm interested in that because I mean if you have different astrophysical sources, right? So if you take, for instance, a neutron star binary merger, then there will be also neutrinos radiated away, electromagnetic fields which contribute. And it will be interesting to have maybe astrophysical data or from models how much of the energy really gets out in what form, and that might also help us with measuring memory to understand more about the source, for instance. I agree with you, but if I identify everything, yes, that I can do that. But if I want to see more of the structures, and I'm interested also in seeing maybe how much energy gets out in what type of source, and how much can we say about the source, for instance.
Yeah.
Okay, well, sorry for asking such a contentious question. Let's move on. So the next
Thank
figure,
you.
let's thank Lydia again.